Welcome. I am Carrie Jennings, Research and Policy Director with Freshwater. Freshwater is your nonprofit watching out for the groundwater and surface water of Minnesota. This will be our 50th year next year in that role. And I'm welcoming you to the Moose Family Lecture Series, co-sponsored by the College of Biological Science and also the Canadian Consulate, Bar Engineering, and the Shingle Creek West Mississippi Watershed Management Commissions. I would like to introduce Paul Connor, who's the Consulate General for the Canadian Consulate here. He covers the states of Minnesota, Iowa, the Dakotas, and Nebraska. And he told me not to read this extensive bio with his impressive career. But he's a great sponsor of our events. And Paul, would you like to say a few words?
Bonsoir, good evening, or as my people also say, good evening, eh? Thank you, Carrie, for that introduction. Thank you to Steve Woods and the Freshwater Society for letting us associate ourselves again and partner with them on this edition of the Moose Lecture. So the Consulate General in Canada, as Carrie mentioned, I get to lead a small but mighty team of 12 women and 5 men, and it's our honor every day to work on deepening all aspects of the Canada-US relationship, which is already the best bilateral relationship in the world between two countries. And let me recognize two of my colleagues that are here tonight, Joel Westman, who works on environmental issues, and Katie DeSanto, who we've just hired away from the St. Paul Chamber, and she's taking up our Arctic file. So I'm happy to have them with me tonight, and please chat with them as well. I'd be remiss if I didn't do my day job and say that the largest issue between our country at the moment is renegotiating our free trade agreement, the NAFTA agreement. On that, let me just say the negotiations, we're into a perpetual negotiation right now, 24/7, 7 days a week in Washington. The negotiations are going well, but we still have a couple tough issues that we haven't agreed on, so not quite sure how it's going to work out. Or as we like to say in my country, the puck is not yet in the net. Okay. On tonight's topic, let me just say climate change is real. It is here, and we need to take action. The Government of Canada is committed to meeting its obligations under the Paris Accord to reduce our GHG emissions arising from human activity, which cause climate change. At home, starting this year at the national level, we've introduced a price on carbon pollution. It's $10 a ton. It will go up $10 a ton for the next 4 years and reach $50 a ton in 2022, at which point the policy will be reviewed. And notwithstanding that federal action, it was already the case before this year that 80% of Canadians already lived in a jurisdiction that was taking action on carbon pollution, because our largest 4 provinces already had their own provincial schemes. Alberta and British Columbia have had a carbon tax for a number of years, and Ontario and Quebec are involved in cap and trade systems, most notably the Western Climate Initiative led by California. I'm happy to tell you on the one hand that Canada's emissions fell by 10 megatons in 2016. We don't have 2017 figures less, but they went down by another 10 megatons in 2016. From the Paris Accord baseline year of 2005, Canadian emissions are down 4%. So the good news is we've got them going in the right direction. The bad news is that is not going down fast enough for us to make our Paris Accord commitment, but let me assure you that Canada is committed to keep working on this to make our Paris Accord commitment. Turning to the Arctic, one of the themes of tonight's lecture, in Canada we are seeing the impacts of climate change in our Arctic. For centuries, the Inuit have maintained a close relationship with nature and Earth. Almost every part of life in Nunavut in our high Arctic will be impacted by climate change, whether it's their traditional hunting patterns, fishing patterns, or gathering of fauna. For example, already some of our native communities have seen their traditional travel routes barred and impacted from changes to climate change, and these routes are no longer accessible. Less access to wildlife, more safety risks from changes in sea ice, from changes in permafrost, conditions, and extreme weather events are all impacting our native populations in the Arctic. Ensuring a healthy and sustainable communities, not only in our Arctic but everywhere, demands that we keep taking action. So with these brief remarks, let me thank Steve, Freshwater Society, and Carrie again for letting us be here. Dr. Francis, I'm delighted to be here with you, and I very much look forward to your remarks. Thank you for being here. Thank you all. Merci beaucoup.
And now just a little more about Dr. Jennifer Francis. She has a BS in meteorology from San Jose State University and went on to do a PhD in atmospheric sciences from the University of Washington in Seattle. She's been a professor at Rutgers since 1994 and has taught courses in satellite remote sensing and climate change issues. She has co-founded and co-directed the Rutgers Climate and Environmental Change Initiative, and presently is a research professor with Rutgers Department of Marine and Coastal Sciences, where she studies connections between climate change and extreme weather. Will you join me in welcoming Dr. Jennifer Francis? Oh yeah, we'll give her a chance. This will give me a chance to get this up here. To get wired up. And I should say she's had a busy day. I think we haven't exhausted her completely, but we've been at a lot of media studios all day long, so.
It has been busy.
Yeah. You will be able to review this broadcast on our website and then look forward to the video of Sven Sundgaard interviewing her about the Arctic this morning, and then she'll be on ClimateCast tomorrow with Paul Huttner.
Thank you. Right, well, thank you, everybody. It's really wonderful to be here, especially to get to know this incredible organization that I didn't know about before, this Freshwater Society, and I know all of you are members, or many of you are, and I'm very impressed by the quality of the people working there and all the good things that you're doing. So it's been a real pleasure to get to know you all today. And I'm really happy to be here. So thank you for coming. I'm glad it wasn't a beautiful summer day, because I know you've been waiting a long time for spring here. That'll be something that we talk about tonight. In particular, in reference to what you're looking at, and I've been told by many people today that this town has a very high fraction of weather fanatics. So you've come to the right place tonight, I'll tell you, because we're going to talk about some crazy weather and what's going on with it and how it's connected to what's happening in the Arctic, and in particular, the rapid melting and warming that's going on up there. Before we do that, though, I'm afraid I have to drag you back to this nightmare that's been yours for this last month. Back in early April. Yeah. It's just really not fair that you get this in April. I feel for you, believe me. I live in Massachusetts now, and our spring has been very, very slow in coming too. In fact, your leaves are out more than ours are, so I definitely feel for you. But, you know, there's an upside. Some people took advantage of this opportunity to create, I'm not quite sure what it is. I think it might be a sea creature, which, you know, from Minnesota, that's creative. But I also know that it's been tough. It's been a tough spring. So, sorry about that. But you should take solace in knowing that you're not alone. There's been crazy weather happening all around the northern hemisphere. This is the coast of England. For the last several winters, they have been pounded by extreme storms. They've broken records in precipitation, which is saying something because their records go back 250 years. Don't feel bad for yourselves anymore. This area in Japan gets a lot of snow, but this particular year in 2012, they broke their record snowfall. And I bet you've got some pretty big house here in Minneapolis, but flooding in Louisiana a couple summers ago broke that record. We've been dealing with it too in the East. The winter of 2014-15 in Boston broke our all-time snow record. We remember Harvey last summer that dumped 50 inches of rain in parts of Houston. Europe has been facing some extreme summers as well, looking at heat waves, forest fires, drought in the southern part of Europe. But if you look in the north, you notice just the opposite, cold, rainy, and wet. You've also heard many, many times about the ongoing drought that's happening in California. They got some relief this year, but it's still a big problem. We had 6 bomb cyclones hit us this winter in New England. And this was a picture of what it looked like in number 5. So just don't worry, you're not alone. And we scientists are not the only ones who are interested in measuring these extreme events. In fact, insurance companies in particular, this is from Munich Re, which is a company that insures insurance companies, keeps track of how many of these extreme events happen because, of course, they're paying a lot of money when it happens. And so this is going back to about 1980, and it's showing 4 different types of extreme events. The red bars there are showing events that are related to what we call geophysical extremes, so tsunamis, earthquakes, volcanic eruptions, things like that. The other 3 colors are representing weather-related extreme events. And what do you notice? The red bars are not changing over time. All the other bars are increasing over time. So all of those examples, including what happened to you this April and this cold winter, have something in common. And this is the kind of extreme event that I'm talking about that's connected to Arctic meltdown. Anybody want to take a guess what that might be? Maybe. All right. So they're all related to the fact that sometimes our weather patterns just get stuck, and we have the same weather happening for a very long time. California drought's a perfect example. Am I still on here? Okay, let's fix this. Okay, good. All right. So, as I was saying, the kind of extreme events that I'm going to be talking about tonight in relation to what's going on in the Arctic are all these types of extremes that are related to very persistent weather patterns, okay? So not tornadoes, not severe thunderstorms, but extremes related to persistent events. If you don't remember anything about tonight, when you go home next year, remember persistence, all right? That's really the key word. All right, so just setting a little context here, I'm sure you're all very familiar with what's been happening to the global temperatures. We're looking at it now going back 1,000 years before today and how the global temperature has been behaving. And what you notice is we were actually on this downward trend for the globe. So all things natural that happen to our climate system were setting us off on this cooling trend until, of course, the recent time, the most recent years here, that red curve. And that's actually kind of behind. And so if you put where we are today, it's really more up in that neighborhood. So clearly what's going on today is not anything like what should be going on in the natural system. It's a big, big effect. And if we look at just the 10 hottest years on record, they're plotted here, and you'll notice that they're all since 1998. Those are the hottest years we've ever measured. Clearly, big change is happening. But what doesn't get as much press, and I think should get a lot more attention, is what's been going on with moisture in the atmosphere. So what we see is going back to the 1970s, we've seen this uptick in the amount of water vapor in the atmosphere, about 7% over that time period. And why do we care about that water vapor? Well, for one thing, it's a greenhouse gas. So it adds to the effect of all this carbon dioxide and other greenhouse gases that we've been putting into the atmosphere. We're getting this increase in water vapor because the oceans are warming, and because the atmosphere, when it warms, can actually hold more of that moisture. So that moisture is not only a greenhouse gas, but it's also the fuel for storms. When that water vapor condenses into a cloud, it releases a lot of heat into the atmosphere. And you probably know that hurricanes feed off of that heat in the ocean. Well, all storms do, actually. And the other thing is that we're seeing this extra water vapor in the atmosphere is contributing to this very strong signal of increasing heavy downpours, heavy snowstorms. And what you notice is that we here in New England and you here in the upper Midwest are seeing the biggest changes. So this is just over the period since 1958, not very long. So if you've thought, boy, it's really been raining harder than usual when we do get rain, you're right, it really has been. All right, so let's get on to the Arctic here. And what we're looking at here is what the ice floating in the Arctic Ocean looked like typically back in the summer of the 1970s and early 80s. And normally back then, the whole middle of the Arctic Ocean was filled with thick, what we call multi-year ice. It averaged about 3 meters thick, or about 10 feet thick. But if we move down here, this is what it looked like during the summer of 2012, when we saw the least amount of sea ice in the Arctic so far. And all this red-colored area here is where the ice is now gone. It's a big, big change. And in fact, we've seen, just based on the area of the ice alone, half of it is now gone in the summer in a 40-year time period. This is just a huge, huge change to the climate system. And because we've lost all that ice, one of the effects of it is that now instead of having a bright surface in that part of the Arctic Ocean, instead now we have dark ocean. And so all of the energy from the sun that comes and hits that bright white ice, which normally gets reflected right back to outer space, never enters the climate system at all. Instead now, in this half of this area, all of that orange stuff is where the energy from the sun is now being absorbed into the ocean and heating the ocean and contributing 25% to the global warming that we've seen so far, just because the Earth is darker now, having lost all this ice and snow. It's a big, big change. So in addition to losing the area of the ice, we're also losing the thickness of the ice. So this animation is showing us how the thickness of the ice, you can see the color scale here, where the yellows and oranges there are the thickest ice, starting in the late 1970s, or 1980 maybe, late 1970s, and going to present up to 2017, you'll see those yellow and orange colors are gone. So if we take that loss of thickness of the ice and multiply it by the area, we get the volume. The change in the volume in that 40-year time period is 3/4. We've lost 3/4 of the ice in the Arctic in 40 years. All right, so one of the impacts of losing that ice, as I mentioned, we gain all that extra heat entering the Arctic Ocean. That's warming the Arctic Ocean, and it's also warming the atmosphere. It's causing the Arctic to warm much faster than everywhere else pretty much on the planet, and certainly faster than anywhere else in the Northern Hemisphere. So here we're looking at the change in the winter temperatures over the Northern Hemisphere. We're over here, and there's Eurasia on the other side there, looking down on the North Pole. Those red colors are showing you that the Arctic is warming much, much, much faster, 2 to 3 times faster. But you also notice this really of blue right over us. The eastern parts of the continents are cooling in the winter, or have been so far. What's up with that? So if we look at how these temperatures, again, have been changing over time, back to the late 1940s, in the Arctic is the blue line here, and the red line here is what we call mid-latitudes. It's down farther south where we all live, 30 to 60 north. What you notice, what I just told you, is that the Arctic is warming much, much faster than the mid-latitudes. And this difference in warming is very important. And we've given it a special name, Arctic amplification. In 2016, that reached an all-time record high, the biggest difference we've ever seen. Why in the world should you care about that? So if we think about a layer of air that extends from here in Minneapolis or St. Paul all the way up to the Arctic, all right? We know that it's warmer here in Minneapolis than it is up in the Arctic, and so we also know that air that's warm takes up more space than air that's cold. So this layer is thicker here in Minneapolis than it is up in the Arctic. So if we were sitting on top of that layer and looking north, it would look like we were looking down a hill. So that air sitting on top of that layer wants to do the same thing that water wants to do when it's sitting on a hill. It wants to flow down. So we get a wind going from south to north, flowing down this hill. All right? Now the Earth is spinning. What it does to everything in the northern hemisphere, because the Earth is spinning, everything that moves gets turned to the right. So this wind that really wants to flow from south to north actually gets turned to the right, and it becomes a west wind. And this is this thing we call the jet stream, this fast-moving river of air high over our heads. And it exists mainly because it's warm here and cold in the Arctic. So now think back to Arctic amplification. What's happening to this layer? It's getting thicker more or faster in the Arctic than it is here. So the result is that hill is becoming flatter, less steep. So there's less force to create that wind that we call the jet stream. And we know that when that wind, that west to east wind in the jet stream weakens, it's more easily deflected from its path by mountain ranges and even surface temperature anomalies out in the ocean. So when the ocean temperatures are different from what they should be. And so we end up with this jet stream that takes a wavier path as it travels around the northern hemisphere. Why would you care about that? Well, we'll get into that. So there are two main effects of this Arctic amplification. That's what the AA stands for there. The one I just told you about, where we have a weakening of those winds of the jet stream. The other one is that we're seeing an intensification of ridges. Ridges are these big northward swings in the jet stream. We'll get to that one in a minute. But both of them basically have the same result. So here on the left is a day in November 2013 when the Arctic was extremely cold. You can see all the blue color there means that it's really cold. That layer of air is very thin. And the jet stream typically in those conditions is relatively straight and strong. But if we have this sort of a situation where the Arctic is very warm, all those blobs of really cold air move southward. And we get this pattern to the jet stream with these much bigger waves, bigger dips to the south and bigger swings to the north. Why do you care about that? Well, it turns out when those waves in the jet stream are small, like in the upper right schematic here, they move quickly from west to east. And when they're big, like we think is happening as a result of the Arctic warming so fast, they tend to move much more slowly from west to east. The reason you care about these waves moving slowly is because those waves are what create the weather. So here's a schematic of a typical jet stream you might see on a TV weather forecast. Right? So this blue curve here is that fast-moving river of wind high over our heads. So the first thing you notice is the jet stream is really the boundary between the warm air to the south and the cold air to the north. So whether you're north or south of this jet stream really puts you in the cold air or the warm air. All right? The other thing is that the dynamics of this wave in the atmosphere are what create high pressure areas on the surface. So if you're under this part of the jet stream, you're in very dry and settled conditions, blue sky, high pressure. But if you're in this part of the jet stream, it's where the motions in the atmosphere are upward. They're creating the storms. It's bringing moisture in from the Gulf of Mexico. And when you're in this configuration, you expect to get a whole bunch of storms. So when these waves get big like this and they move slowly from west to east, you're going to get stuck in one of these patterns, depending on where you are relative to the wave. Okay? It's so sad that the real world doesn't look nice and simple like that. This is what the real jet stream looks like. These are real winds plotted by NASA's Science Visualization Studio. It's about 2 or 3 weeks worth of data. And the yellow and red colors there are where the winds are strong. So you can see very clearly where the strongest winds are and where that jet stream is. All right, so we're over North America now. So I want you to notice first just how god-awful messy it is. All these swirls and waves breaking up, and sometimes those waves are small, like here when they're moving quickly from west to east. And then sometimes those waves get big, like that, and they really don't move very much at all. All right, so this is the real atmosphere. So how do you go about, as a researcher like me, trying to look at this real-world data and decide or figure out whether, in fact, we're seeing this expected relationship between Arctic amplification affecting the jet stream the way we think it is? Well, I'm just going to give you a really brief taste of some of the research we're doing, because we don't have a lot of time tonight, but I'm just going to give you a little snippet of one of the simpler ways that we're trying to get at this. So I'm pretty sure most of you have looked at a topographic map sometime in your life. I know there's not a lot of topography right around here, but hopefully you've looked at a topographic map. So we can take that layer of the atmosphere that I told you about in the beginning there, and we can map it just like you would a topographic map. So where these colors are red, it's where that layer is thick because the air is warm. Where the colors are blue, that's where it's cold, and so the layer is thin. And what do you know about when the lines are really close together on a topographic map? It's really steep, right? So that's where the jet stream is, where those lines are really close together. Okay? So let's zoom in on North America here. Same map, just zooming in. Here's Massachusetts, there are the Great Lakes. So this is just one day in January 6, 2014. It was a famous day because that's when the whole world learned about the polar vortex, and we were attacked by it in the east. So we've got these maps of data going back for the atmosphere 4 times a day, ever since 1948, right up to present, which is like a gold mine. So what we do is we pick one of these lines, okay, one of these lines of constant height in the atmosphere. And we pick it so that it falls right in where that steepest part is, so where the jet stream is. And every single day, we measure how far north it extends, how far south it extends, and the difference between that. And when that difference is really big, we call it a big wave. And then we count how many times per season we get big waves, or per year, or whatever. And you can do it in different regions or for the whole northern hemisphere. If we do it for the whole northern hemisphere and we keep track of how many times that happens, in this case during fall, we get this green line here, which is the frequency of really big waves. And what do you notice? It's going up. Also plotted on here, that black dashed line is the speed of the west winds of the jet stream, and it is going down. So both of those things seem to support this hypothesis that we came up with back in 2012. So if we zoom in now just on the North Atlantic, we see an even bigger uptick in the frequency of these big waves and an even bigger decline in the speed of jet stream winds. So this just to give you a little taste of the kind of metrics we're working with. And now I want to get back to that other arrow that I showed you of how Arctic amplification affects the jet stream. And it's this new hypothesis that we just published, and we call it, it takes 2 to tango. And the way it works is, if you think about the good old days when here's North America, here's the Pacific Ocean, back in the good old days when the Arctic was filled with all that nice thick ice, And this wave in the jet stream comes along, and there's really no impact on it because the ice is pretty much the same from year to year. But fast forward to today, and oftentimes we see a big chunk of ice missing from the Pacific side of the Arctic Ocean. And as you know now, when we lose all that ice, we gain a lot of heat during the summer, and then during the fall, all that heat is released back into the atmosphere. So what happens if a wave in the jet stream comes along, happens to be located right here? The ice loss has no effect because that peak in the jet stream is not located where that extra heat source is in the Arctic. And different temperature patterns in the Pacific Ocean tend to set up these waves in the jet stream in certain places. But lately, what we've been seeing is a tendency for the wave to be located right about there because there's a lot of warm water piled up along the west coast of North America and has been since late 2013. So now what happens, this ridge in the jet stream comes along. It's located right where all that extra heat is. And what happens? It pumps up that ridge. It makes that layer thicker in that location. The wave is now bigger. And what do we know about bigger waves? They move more slowly. So we're seeing this tendency for a very persistent pattern with this big ridge in the west. Remember, this is the dry part of the wave, so it's contributing to the drought in California. We know all the cold air is north of the jet stream, so we're tending to see this cold winters in the east. And this is the stormy part. Those 6 cyclone bombs that we had this winter came from that exact pattern. So this is a new hypothesis that connects an aspect of climate change, which is the loss of the ice, with natural fluctuation patterns that happen in the oceans. All right, so I know there's some pretty geeky types out in this audience, so I'm going to get down in the weeds a little bit for you guys as kind of like a last thing. And so we're going to talk about this hypothesis of it takes 2 to tango and how it's emerging on the Eurasian side of the Earth, okay? And you'll see that there's a bajillion papers listed here. This has been identified in many papers. We're really quite sure that this is a robust mechanism that I'm going to tell you about here. All right, so starting in September, this is when ice is at its lowest extent, and continuing on through February, this is how we think the story goes. So here we are in Europe. There's a mountain range right here in western Russia, the Ural Mountains. And those mountains tend to create a ridge in the jet stream. That blue thing right there is the jet stream. So we have a climatological ridge that tends to exist right about there. So also right about there in the Arctic, this area is one of the places where ice has been disappearing the fastest. So what's happening? That ridge is getting enlarged. It's getting intensified, just like I told you. And what happens when that ridge gets more intense? It tends to create a strong high pressure at the surface. Those surface winds bring a lot of cold Arctic air down over Siberia. With it comes a bunch of moisture, creating a whole bunch more snow, and also depressing the jet stream farther south. Okay? The overall story there is it's a bigger wave now, all right? So it's a very persistent pattern. So there's that stronger high pressure and a lot of snow, depressed wave. So what happens when the jet stream gets wavy in the wintertime is it transfers a bunch of that wave energy up to the true polar vortex. The true polar vortex lives in the stratosphere. It's not what you heard in the media in January of 2014. It is actually up in the stratosphere, all right? So when that wave energy gets sent up there, it disrupts it and makes it, see how it's all donut-shaped here, later in the winter? So that is like a memory mechanism in the atmosphere that hangs on to that waviness, if you will, and then transfers it back down to the jet stream later in winter. So this mechanism that started way back in September has this mechanism that carries it well into late winter. All right? And this is an example of this "it takes two to tango" idea. All right, so let's get back to the present here before we wrap up. And as you probably know, we've been suffering, just like you in the East, snow in Jacksonville, Florida. My phone was ringing constantly. The iguanas were freezing and falling out of the trees. So what did the jet stream look like? Can you picture it in your mind? This is the average jet stream shape during this past January. Really warm out west. You were cold, we were stormy. And then there's you poor Minnesota here with your icebox in April, just not fair. Record low temperatures for the first 2 weeks in your region. What did that jet stream look like? Just what you'd expect, right? But then in February of 2017, we don't have to go very far back in time to see a totally different story, but for the same basic reason. The jet stream was in a different location this time, and it created this area of record warm temperatures. So we had this big ridge in the jet stream over North America. All right? So now you guys know everything there is to know about jet streams. The good news is that overall, your winters are warming. It's going to get a little easier here probably. But we'll see. You know, this whole jet stream idea is unraveling and unfolding as a result of at least partially because of what's going on in the Arctic. So this may turn that number around a little bit in the next few years. So just bring this back to the Arctic one more time. This is a plot of going back to November of 2017, so just past November. We're looking up into the atmosphere now, so starting at the surface, all the way up to the stratosphere. And these colors here are showing when the Arctic had pulses of extreme heat through this past winter. All right, so you see it's not a nice regular warming at all. It actually has these episodes of when the Arctic atmosphere, all the way up to the stratosphere sometimes, has been much warmer than normal. So these are all differences from normal. So now if we match up some of the extreme weather events that happened this winter, what we notice is they line up very well with these pulses of heat in the Arctic. So there's all kinds of extremes here. There's record cold in the Northeast. There's bomb cyclone, California heat wave, extreme cold in Canada. And here's our series of nor'easters starting in the East Coast. So we see this relationship. It's certainly not proof, but it certainly seems to suggest that the Arctic has something to do with it. So what about the future? Well, we can look at how the sea ice has changed in the real world, which is the black line here. This is the extent of sea ice in the summertime. And we can compare it to what climate models both say about the past, they match it pretty well, and what they say about the future. And you can see that the future has several realities shown here in different lines. So overall, the red line here is what we will get most likely if we do nothing in terms of reducing our emissions and continuing along as we are. And it's good news to hear that Canada is making so much progress, but I would like to see some of that progress happening here as well, because if we don't, we're going to lose the rest of the ice in the summertime in the Arctic. Probably, this is actually even a pretty optimistic graph, but we're looking at somewhere in the 2040 range. But the good news is it's probably not hopeless. You know, if we do work hard and reduce our emissions and can figure out how to extract carbon from the atmosphere, then we could save some of the ice in the Arctic and prevent some of these extreme events related to Arctic warming from being quite as bad as we expect them to be. So with that, I think we're ready to take some questions.
That serves as a reminder for you to write your questions on using the Pigeonhole Live app, which you received a flyer for as you entered. We've got a few questions. We'd like a few more. We are going to be putting some chairs up here on stage, and we'll be joined by Dean Valerie Forbes of the College of Biological Sciences. You can start making your way up, I think, Valerie. Dean Forbes has a PhD, an undergraduate degree from Stony Brook, and a PhD, I guess that is your PhD. She called herself a marine scientist earlier. I know she works on the effect of toxic chemicals on sea life, many organisms from the molecular to the organism scale. Why don't you come on up, Valerie, and we will get you situated here. But please take this time to enter your questions in Pigeonhole or vote for the ones that exist already. And we'll get you can put that back on.
So we're going to get some questions from the audience. Thank you, Jennifer. That was fascinating. I thought that you really, one thing we hear a lot of is this confusion between weather and climate.
Right.
And I think you just explained that beautifully. Let's just go into the questions. So what long-term trends do you anticipate in the Arctic, I'm forgetting.
Oh,
Arctic application, thank you. In the future based on what we know now?
Great question. We expect Arctic amplification to continue to increase, unfortunately. It's a very consistent simulation by all the different climate models that this is going to continue to get just larger as we lose more and more ice. Even after the ice is gone in the summer, that energy will still go into the ocean and warm the ocean up even longer or even more. And the ice-free season will continue to get longer and longer. So even after we lose all the ice, we expect it to continue to increase, sadly.
So more polar vortex attacks.
That's where my money is.
Okay. What about the Gulf Stream? You didn't mention anything about the Gulf Stream. One of the things I've heard is that one of the effects of global warming is that the Gulf Stream will slow down and eventually stop because of the difference in temperature that drives the ocean circulation.
Right.
Which could put Northern Europe in a much colder place.
Yeah. So we are seeing some signs of the Gulf Stream slowing down. And it's related to an increase in fresh water that's flowing both out of the Arctic Ocean because the precipitation in high latitude land areas is putting more water into the rivers that flow into the Arctic Ocean, also losing the sea ice. But more importantly, the addition of fresh water from the more rapid melting of the Greenland ice sheet. So all that fresh water sits on top of the ocean really because it's lighter than the saltier water underneath it, and it prevents mixing from happening in that upper part of the ocean. And one of the main drivers of the ocean circulation system globally is the formation of this very heavy, salty, cold water when ice is formed in the North Atlantic. And so if we've got this layer of fresh water sitting there and not stopping that from happening, but definitely slowing it down, then there is an indication that, and they've even measured an apparent slowdown of that circulation in the North Atlantic at least. But I think I would have to say that probably the warming is going to overwhelm any cooling that might happen. So what it will probably do is reduce the warming that would have otherwise occurred, not lead to an ice age in Europe anytime soon.
Good news for our friends in Scandinavia. All right, next question. Is there an Antarctic effect that is equivalent?
There is not. So the Antarctic situation is completely different, and that's why I study the Arctic and not both, because they are so different. And most people, there are very few people who are, we call them bipolar, when they... Not many of those in my community. So, so the deal in Antarctica is that, the Arctic is an ocean surrounded by land. Antarctica is land surrounded by ocean. But the land down there has a couple miles of ice sitting on top of it. And they do have sea ice that forms in the winter around the continent of Antarctica, but every summer it melts almost all the way back to the coast. So you don't have this opportunity to lose a whole bunch of ice, gain a lot of energy, heat into the ocean, and set up this vicious cycle that we see happening in the Arctic that's leading to Arctic amplification. Okay. So that process just doesn't happen. Okay. The other thing is that Antarctica is much, much colder. And so warming the globe even 2 or 3 degrees is not going to melt a lot of ice yet on Antarctica, whereas Greenland is much closer to the melting point. So
there aren't signs that we're losing ice from the Antarctic?
So we are, but for very different reasons. So the oceans are warming, and warmer ocean water is actually meeting up with the glaciers that are coming off of the Antarctic ice sheet. So they're melting from underneath.
I see, okay.
And the concern there is that a lot of those ice shelves that come from the ice sheet are acting almost like barriers that keep the ice sort of keep it up onto the land. And the concern is that if we lose enough of those ice shelves, that it's going to be like taking the cork out of a bottle of champagne, and all of a sudden we're going to see much faster flows of ice off the Antarctic ice sheet, and sadly we're already seeing that happen.
Okay, and that's going to presumably lead to increased sea level rise, and all that good stuff as well.
Yes, all that good stuff.
Yeah.
Yes.
Okay. All right. So, as the different levels of the atmosphere start to become more even across the latitudes, what will happen with the jet stream? And are there projections on when it might level out?
So the Arctic is always going to be colder than it is here.
Good.
Yes. It's always going to be 6 months of dark winter up there. So we're going to have sea ice in the winter up there for a very long time. So we're always going to have some hill in the atmosphere, especially in the winter. And especially if we start warming the land areas quite fast too. So this helps, bump up that hill a little bit that would be flattened out by the Arctic amplification. So we will see a continuation of the Arctic amplification and the flattening of the hill, but the hill's not going away.
Okay, so it will never level out, in other words.
No, and another sort of interesting twist to this story that I didn't want to get into too much, but there's another area of amplified warming in the atmosphere, and that's called tropical amplification, and that's happening in the tropics, but at high levels in the atmosphere. It's actually not been observed yet, but most of the models project that it's going to happen. So there's actually 2 jet streams in the wintertime. There's a polar jet stream, which is the one I've been talking about mostly, and sometimes there's another one called the subtropical jet stream. And that subtropical jet stream is also formed by a similar hill in the atmosphere because the tropics are warmer than the mid-latitudes. So if we warm the tropics even faster, if the models are right, then it's going to actually make that hill get steeper. So we're going to see a strengthening of the subtropical jet stream. So there's this tug of war emerging in the atmosphere, and that's partly why there's still quite a bit of controversy about how all this is actually going to unfold and whether the tropics are going to win or the Arctic's going to win.
And when you say win, what do you mean exactly?
Overwhelm the other effect.
Okay.
So which effect is going to win out and be the stronger one? And there's still a lot of debate about that in the research community.
Okay, and I mean, could you explain that a little more? Like, what would that do? So if the tropical one became stronger, what would that do to the temperate?
So it would probably, so when we see the Arctic warming a lot, and I showed those 2 examples of when the Arctic was really cold and the jet was straight, and then when the Arctic was warm. Well, one of the things that happens is the jet stream actually shifts southward on average.
Right.
So if the tropical amplification is the stronger one, then it has the opposite effect. It tends to move the jet stream closer to the poles.
Okay.
So it would offset some of the effect of Arctic amplification.
And that would make the persistent weather patterns in this part of the world less, potentially? Less persistent? if it's moving
It
north?
could.
Okay.
This is still really
Okay,
new stuff,
yeah.
and different models are giving us different answers, and
Yeah.
so there really isn't a good conclusion to draw yet.
So how do, I mean, I'm glad you raised that, because it is confusing for non-scientists to
There's
kind
a
of
lot of
appreciate
things
that-
going on, yes.
I mean, not only this connection between weather and climate, especially, and I'll hear family members that say, well, how could it be we're having global warming because it's, we've had the coldest winter ever, et cetera. But
Now you can all
also,
answer that question, right?
now, right,
Yes.
now we have the answer. But also to explain, we have these models, but there are uncertainties there, and the different models project different things, yet this is,
For some things, they're different, but
Yeah.
there's many, many signals that they are consistent on. So we've got the sign right on, or the sign is confident on a lot of the changes that we expect to see in the future. Things like ice disappearing,
right.
things like the continents warming, things like the oceans warming, many other things. But there are some of these very complicated mechanisms that have a lot of moving parts, and they're all changing simultaneously, and it's really not sure how they're going to interact with each other. So we still have some surprises, I think, in our future.
For sure, for sure. Good, all right. Let's see. I'm paraphrasing the audience, I've heard of strategies that look to cover ocean with giant white sheets of plastic. To increase albedo seems a bit far-fetched, but would something like this actually work? I thought we were trying to get plastics out of the ocean. Did I miss something?
So a more realistic version of this is to use a silicate product, which is an inert but very white powder, and sprinkle that on the ice and increase its albedo, which is the reflectivity of the ice. This is a serious,
Really?
I'm not in favor, but it is something that is being discussed in a serious way. The problem is, once you start doing this, and this is really just treating a symptom, it's not
Right,
getting at
yeah,
the underlying
yeah.
disease.
That's right, yeah.
So you may be able to prevent some ice loss for a while, but as soon as it rains,
Yeah.
these particles are going to wash off into the ocean, and they are inert, so they shouldn't do any real damage. But it's got to be this ongoing campaign that every single or 2 or 3 times a summer you have to go out there and sprinkle these particles, and that's going to cost a lot of money. It's going to take our eye off the ball of
Yeah.
actually
Yeah.
working on the disease rather than putting a Band-Aid on a symptom.
And given the scale at which you'd have to do that,
Yes.
isn't it just easier to reduce, greenhouse gases, kind of?
Easy?
Maybe? I mean,
It's necessary,
Yeah.
for sure. It's expensive, and it would
Sure.
be taking resources away from doing a more permanent change in our behavior that would actually help
Yeah.
not solve the problem, but make it less bad.
have you heard of any other crazy or less crazy solutions that are being
Oh,
discussed?
yes.
Oh, do tell us.
So another idea is to put little particles that are like little mirrors up into the stratosphere and reflect the sun before it even gets to the surface.
Okay.
But do it in, globally, or at least in latitude belts where they would hang out up there for a long time. There's other plans to put ships up in the Arctic Ocean to suck up seawater and spray it in little droplets up into the atmosphere to increase the cloud cover. Same ideas. We're trying to increase the reflectivity some way to send more of the sun's energy back to outer space. But again, all these things are Band-Aids on the symptoms and expensive. And as soon as you stop doing any of them, all of those greenhouse gases have been building up in the atmosphere, so you're going to have this even bigger spike in temperature if you stop.
Right. Which one of the things that you mentioned is, humidity as a greenhouse gas, which I think that's the first time I've ever really heard that phrased that way.
It's actually the most important greenhouse gas. You don't hear about it because it's
Not
natural.
at all. Well, carbon's kind of natural too, but I mean, and you
But
think
the
about
increase
right.
of carbon has gotten all the attention, whereas
But it must be a more indirect. So the carbon is a more direct result of human activity,
that's true.
whereas the humidity is sort of it would
It's a
seem to me
result of the
a result of it,
evaporation
right.
and
Because it doesn't seem there's much we could do directly to affect the humidity as we can for other greenhouse gases, for example.
right,
methane
other
or-
than just not warming as much.
Well, yeah,
Yes.
yeah, okay,
Mhm.
okay. That's
Yeah.
kind of interesting. Okay. Let's see. Is this primarily a springtime impact rather than a fall impact? So these extreme weather events?
No. In fact, spring and fall are probably lesser in some ways because they tend to be a very chaotic period in our weather. I mean, we get these big extremes in spring and fall typically. So it's really winter. The winter season is when the sea ice has the biggest impact on the atmosphere. And if you remember that series of globes that I showed and how, moving through the winter time, the reason it has the biggest impact is because the air is very cold in the Arctic during the winter. And if you have open water exposed to it, you have a huge temperature difference. And so you get a lot of heat dumped into the atmosphere from the ocean
Okay.
and moisture.
Yeah, okay.
So
Okay.
that's when you get these, the biggest impact on, say, making these ridges more intense or something like that. So I didn't talk about summer much because it's another complicated mechanism that's unfolding. But what we're learning about summer is that it's not so much the sea ice loss, it's the snow loss in the spring on high latitude land.
Okay.
And we know that the snow is disappearing even faster in the spring than the sea ice is disappearing in the summer in terms of area. And the reason that's important is because as we lose that snow cover earlier in the spring, and we're talking about weeks, I mean, it's a big, big signal, then the soil underneath that snow is now exposed to very strong spring sunshine. And so it dries out faster, it warms up earlier, and it warms the atmosphere earlier. So it kind of gives a jump to summer conditions. The other really interesting thing is that it sets up a double hill in the atmosphere because we have this stripe of Arctic amplification
Right.
along the northern tier of the land areas. And when we get this double hill in the atmosphere, we get a split jet stream. This gets complicated, I'm sorry.
It's okay. No, don't
But,
apologize.
when we get a split jet stream in the summer, it tends to trap the waves
Yeah.
and sets up these very persistent conditions. So like the heat waves they've had in Europe, 2003, 2010, flooding in Pakistan, these very persistent summer patterns, especially in Europe and Asia, have been tracked down to these split jet conditions.
Okay.
And we believe it's related to the loss of the snow earlier in the spring and setting up this double hill in the atmosphere.
Okay.
This is all brand new stuff, I'm telling you.
It's very cool. Do you think this is likely to shift our seasonal weather patterns, so to make either earlier springs, despite what we experienced a few weeks ago, or later springs, or is that not
Well,
related
I
to
mean,
this?
overall, there's a warming, right?
Right,
So
right.
spring is overall, long-term average is going to come earlier, however you want to define spring.
Okay.
Um,
Lack of snow helps, but
It's a good thing.
there are other signs.
Yeah, I mean, literally everywhere except the Midwest and the East this spring has had a very warm early spring. In fact, I think it was the second warmest April on record
Wow.
globally.
Okay.
So we are an anomaly,
Yeah.
but we think we know why.
Yeah.
So
Okay. Very good. Let's see.
these are great questions.
What is a good economic argument for action? I liked your insurance graph
Well,
is maybe one, perhaps.
We just had the most expensive, year of weather extremes in the United States
Yeah,
in 2017.
for sure, yeah.
If that's not an economic reason to act, I don't know what is.
You would think. Those numbers are pretty high.
I mean, sea
frighteningly
level,
high.
Miami's shelling out hundreds of millions of dollars to try to preserve their city as the tides continue to rise and flood the streets on a regular basis. Same in Norfolk, Virginia.
Yeah,
The military is very concerned. They've got, especially the Navy, has a lot of infrastructure at risk. Places like Norfolk and Southern California and places like that are all gearing up for trying to protect their assets.
well, and I think it is those extreme events, right? It's
It
not
is.
going to be the small average increase in temperature or the gradual average increase in sea level. It's those extreme storms that are going to do the economic damage.
Yep.
So, yeah.
Yep. And we're all paying for it, you know?
Right, exactly, exactly. So, all right, good. How are insurance companies responding to the increases in weather-related loss claims? Anyone's premiums going up?
Absolutely.
I mean,
Absolutely, they're going up. And, you know, flood insurance may be a thing of the past.
yeah, yeah.
The government wants
to.
to get out of the flood insurance
Yeah.
business. And that means private company's going to come in, and it's not going to be cheap.
Right, right. I don't know why this should remind me, but thinking about all of these waves and jet streams
Does
and
that make
things.
anybody seasick? Maybe?
No, no. I was wondering if there are any implications for aviation that you know, pilots and things have to worry about if you have that. I mean, they
You
slow
know-
you down. They can slow you down if you have a really strong jet stream.
If it's really
If you're
strong, it
flying,
would slow you
yeah.
down. But they're pretty good at avoiding those really strong jet streams. They, you know, they are
Fly
very
around 'em.
tuned into what the jet stream is up to because they want to be in it if they're going in
Yeah.
west to east, and
Yeah.
they don't want to be in it if they're going
Yeah.
east to west. So,
Okay. So they're just, they can work around. They can
Yeah.
map them, and you know where they're going to be, and so
Yeah.
you can just work around.
there's been
them.
some
Okay.
suggestions. A couple of papers have come out suggesting it might become more turbulent. But
Oh no,
it's,
I hate turbulence.
I know, but you know, I think there's not a big strong case to be made with
Okay.
robust changes happening with that.
All right, good. Any more? What do the models show between the relationship of Arctic ice loss and sea level rise?
Right, that's a great question because sea ice is floating already. So if you take a glass of water with a bunch of ice in it and you mark where the water level is in your glass of ice, and then you let that ice melt, that water level will be the same. So when we melt sea ice, we are not directly affecting sea levels. However, that word directly is important because, as I explained, the loss of the sea ice is increasing the rate of warming, especially in the Arctic. And so that extra warming that's happening in the Arctic is accelerating the melting of Greenland. And it's accelerating the melting of glaciers. And it's accelerating the warming of the oceans. And right now, those are three of the main factors that are causing sea level rise. So those are indirect effects.
Yeah, yeah. And how much do the models vary in terms of sea level rise expectations? Are they pretty
For
close?
the future?
Yeah, yeah.
So the uncertainties in that are all about us, what
Okay.
we do in
Yeah.
the future.
Yeah.
So, you know, the models can simulate what's going to happen if we stay on the course we're on now, emitting as we are,
Right.
or they can simulate what happens if we're able to go off of our fossil fuel addiction.
Okay, but I mean, in terms of the relationship between the melting and the sea level rise, I would think that was much more, or much less uncertain.
There are a lot of pieces of that that
Yeah,
are still
okay.
quite uncertain. So in particular, the melting of the undersides of glaciers coming off of the Greenland ice sheet, for example, and Antarctica for that matter. So, you know, some of those pieces don't have, you know, good hard numbers on them, but, you know, it's one of those things where the sign is very clear. It's just how fast.
Yeah, yeah. Okay. Good. Have we come to the end of our questions? Where's Leslie? Oh. Okay, a couple more. What evidence are you looking for to prove or disprove your takes two to tango hypothesis?
So that's...
You gotta like the name.
Yeah, I know. It's pretty catchy.
Yeah, very good.
So it's going to take probably some targeted modeling studies where we can control how many things are changing in the climate system at one time in a climate simulation. So we can change things like realistic variations in ocean temperatures. We can shift where the ice is lost from one area to another area and then see how the model responds in terms of what the atmosphere does. So that's going to be a good line of evidence if we can simulate those. And there are a couple papers out that have done that, but we need to build up that body of evidence to a nice big pile.
It's nice to hear you have so much data available to analyze.
Of the real world, yes.
Yeah, and over a relatively long period of time.
Yes,
So-
but we need to think about new metrics, new ways to use that data. So, for example, this very simple method that we came up with to measure the size of the waves and how often we have these big wave events. You know, people just never looked at it that way before. They would average over, many years, over big areas, and in terms of model simulations, over many model simulations. And then if you've got one of these big wave patterns, but it's not always in the same place, then you're just going to lose any signal of this effect. And so, we've kind of got to retool our brains. How are we going to get at measuring this thing? So, one of the other ways we're doing it is borrowing from the research on rivers, and they have a metric called sinuosity, which Carrie mentioned today. And we've adopted that metric to use with these lines of equal height going around the northern hemisphere, and using that metric to say, okay, how wavy is it? In a very similar way that it's used for rivers.
A good plug for multidisciplinary research. I like it.
Exactly.
All right. What do we got? Do we have any more? Last one. All right. What is happening that you did not anticipate?
The speed.
Okay.
How fast things are changing, especially in the Arctic.
Yeah.
We expected to see the ice gradually disappear. That was what's going to happen as the globe gets warmer. We didn't expect it to happen this fast. And there are a lot of other aspects to changes up there. We're seeing big shifts in the biology as well. So as we lose that sea ice once again, we're letting a lot more light into the ocean in the Arctic. Algae are blooming earlier and in places where they weren't blooming before, and that's the base of the food web. So we're expecting some big surprises in the ecological side of this story. And in fact, I think that's where the biggest wild cards are, is just how the ecosystem is going to respond to this incredibly rapid change that it's really never seen before.
Yes, that's a job for biologists.
Yes, more interdisciplinary.
Yes, there we go. Good, excellent. So just as a final question, where are you going now with your research? What are your next steps to address these issues?
So one avenue that we're working on right now is trying to figure out ways to measure whether, in fact, weather patterns are becoming more persistent.
Okay.
I mean, that's sort of like the bottom line there. And that sounds straightforward, perhaps, but it's really not, because we're trying to measure whether these regimes are more persistent. It's not, at one place. And so, you might think, oh, we'll just, take the temperature at one station and see if it stays the same for a few more days more often or something like that. But, temperature is a terrible variable for that, because it's affected by cloud amount and by the wind direction and whether the soil is moist. And there's many, many things that go into a temperature, whereas the pattern overall could be the same while the temperature is doing all kinds of things. So we're working on new metrics to get at that give us a better handle on whether we in fact are seeing these more persistent weather patterns.
Excellent.
That's just one example.
Yeah.
I'm doing a lot of different things, but yeah.
Well, good. Well, it's fascinating. And
Thank
I
you.
wish you continued success with it. And thank you for sharing with us.
My
Thank all
pleasure.
of you for your attention. And have a good evening.
Thanks.
Really cool stuff.